Welcome back to the Deep Dive. Today we are wrestling with one of modern science's most confounding and, frankly, explosive figures, Kary Mullis. Born in 1944, passing away in 2019, Mullis was the American biochemist who gave the world an invention that, and this isn't an exaggeration, fundamentally changed the physical science.
It really did. We're talking about the polymerase chain reaction, or PCR.
PCR. It's the ultimate tool for amplification, not just scientifically, but,
Yeah.
I mean, metaphorically, too, when you look at his life.
That's a great way to put it. The New York Times, when they were discussing his work, used this just a magnificent line.
Yeah.
They said his invention virtually divided the field of biology into two distinct epochs. Before PCR and after PCR.
And that's not hyperbole.
Not at all. PCR is the bedrock of, well, almost everything we do today. Forensics, rapid diagnostic testing, cutting-edge genetic research, even phylogenetic studies. It's everywhere.
But the core mission of this deep dive isn't just to celebrate the Nobel Prize winner. It's to try and understand the man behind the invention.
Right.
Because Kary Mullis presented this intense, almost unbearable contrast between his certified Nobel-winning scientific genius, I mean a total mastery over molecular structure, and his highly unconventional, often deeply controversial views.
We've used an exhaustive biographical account to really explore this full spectrum. We'll trace his path from, high school rocketry and some clandestine chemistry.
You get to that.
Oh, we will. All the way to his breakthrough at Cetus Corporation. And then we have to dive deep into his profound and sometimes dangerous skepticism on huge public health issues like HIV/AIDS, environmental science like climate change, and even his documented belief in the outright paranormal.
We're talking about a man who gave us the ultimate instrument for revealing objective truth at the molecular level.
Yes.
Who, in his personal life, was completely comfortable entertaining this scientifically implausible. This includes a widely publicized account of an encounter with a fluorescent talking raccoon.
A fluorescent talking raccoon, he suggested, might have been an extraterrestrial alien. You can't make this stuff up.
You really can't. It's a true study in paradox. The genius who, as one biologist put it, superpowered molecular biology,
Right.
was at the same time guided by anecdotal evidence and personal belief whenever he stepped outside his own domain.
And that's why this deep dive is so crucial for you, the learner. We're trying to help you understand a true intolerable genius, a case study in how world-changing innovation sometimes springs from the most unexpected and, sometimes erratic places.
So what does it mean when the man who gave us the power of molecular certainty was himself so uncertain about established reality?
Yeah.
Okay, let's unpack this life story, starting right at the beginning.
So Kary Mullis was born in Lenoir, North Carolina, but he spent his formative years growing up in Columbia, South Carolina.
Okay.
And his early life, it was really marked by this deep fascination with the natural world. He spent a lot of time just observing organisms, which, reflects a foundational interest in biological systems. His family had a farming background, but his own curiosity just pulled him toward the hands-on world of chemistry.
And when you say hands-on, his chemistry interests were anything but theoretical. We're talking about the 1960s here.
Right.
Personal rocketry was a pretty big hobby for aspiring young scientists back then. Mullis wasn't just reading about it, he was actively involved in chemically synthesizing and building solid fuel propulsion rockets.
In high school.
In high school. This early mix of, intellectual rigor, practical chemistry, and a willingness to embrace risk, or maybe just the sheer fun of making things go boom, it feels like a crucial foundation for how he approached problem solving later on.
Absolutely. And he channeled that energy into formal academics. He got a Bachelor of Science in Chemistry from the Georgia Institute of Technology in 1966. And it's worth noting, his life was already moving fast. He was married for the first time while he was still an undergraduate, and he was already dabbling in starting these small businesses. His path was accelerated and nonlinear from the get-go.
He didn't slow down for grad school either. He heads to UC Berkeley for a PhD in biochemistry.
A big deal.
A very big deal. And his doctoral work, which he finished in 1973, was highly specialized. It focused on the synthesis and structure of bacterial iron transporter molecules, technically called cytophores.
Specifically, he characterized one called schizokinin.
Okay, let's break that down. Cytophores, what are they doing exactly?
So think of them as molecules that microorganisms like bacteria secrete to basically scavenge for iron in their environment.
Like little molecular claw machines.
That's a perfect analogy. Iron is essential for microbial growth, but it's often locked up in forms they can't use. Cytophores go out, grab the iron, and transport it back into the cell. Mullis's work was on characterizing the structure of one of these. It was precise, rigorous chemistry.
So he's clearly operating at this really high level of chemical complexity.
Yeah.
And yet there's this recurring story that he really struggled with the formal academic structure at Berkeley.
He did. His time there was notoriously difficult in terms of him fitting the mold. Colleagues noted his unique style, but also his struggles with standardized things like oral exams. Yeah, one recalled that he struggled badly with his oral exams. He said Mullis, quote, didn't get his propositions right. He didn't know general biochemistry. The formal discipline of academia it chafed against his intuitive, unconventional way of thinking.
And this tension became very real when it was time to submit his thesis. We have this incredible detail that his dissertation was only accepted after his friends had to intervene.
They literally had to cut all the wacko stuff out of it.
Which speaks volumes, right?
It really does. The core chemistry on schizoquinin was solid, but Mullis's tendency to integrate these, far-out philosophical or totally unrelated scientific tangents into his formal work was already there. He was a brilliant chemist, but he resisted the structured confines of the scientific establishment from day one.
And if we need any more proof of just how eclectic his mind was, think about this. 4 years before he even got that biochemistry PhD, back in 1968, he published a sole author paper in Nature.
Which is almost unheard of for a grad student.
In Nature. And the topic was a whole different ballgame. It was astrophysics. The title was Cosmological Significance of Time Reversal.
A biochemist writing theoretical astrophysics in Nature. It shows he was either breathtakingly confident or a genuine polymath, or, maybe a bit of both.
And yet, after he gets his PhD in '73, his career path just takes these surprising, almost aimless detours.
It really does. He did a couple of postdoctoral fellowships, first in pediatric cardiology, then pharmaceutical chemistry.
Then he just leaves science.
Completely. He managed a bakery for 2 years.
A bakery.
A bakery. And then he left the technical world entirely to try and write fiction. This is not the resume you expect from a future Nobel Prize winner. It really emphasizes how much chance and a little push from a friend played a role in bringing him back to the lab. And that return to science was directly orchestrated by his friend and former colleague, Thomas White.
Okay, so White's a key figure here.
He was instrumental. First, he helped Mullis get a postdoctoral position at UCSF, and then he facilitated his move to Cetus Corporation in Emeryville, California. Cetus was one of the early major powerhouses of the biotech industry.
And Mullis arrived there in 1979 as a DNA chemist. It's important to remember, as we said, he had very little formal molecular biology experience at this point.
Right, but he was a highly capable synthetic chemist. He ended up heading their DNA synthesis lab.
He spent 4 years there, and then in 1983, we get the legendary Eureka moment.
This is the moment that changed everything, and the setting is almost mythological now. Mullis was driving late one Friday night. He mentions the time was about 10:30 p.m., heading out of Berkeley toward his country home in Mendocino County. He was with his girlfriend at the time, Jennifer, who was also a chemist at Cetus. He's driving on Highway 128, going past a winery, and then the idea just hits him.
So what was the specific problem he was trying to solve in his head?
He was trying to figure out a method to detect a single, very specific base sequence within a massive, complex sample of DNA, like the entire human genome.
Which was the holy grail at the time.
It was. Before PCR, if you wanted to study a particular gene, you had two main options. You could either grow the DNA inside living organisms, a process called cloning, which was slow, labor-intensive, and needed specialized cell cultures.
Sure.
Or you could use these time-consuming, chemically complex sequencing methods that could only analyze tiny little snippets. Getting enough clean, specific DNA to study was the bottleneck.
It was like trying to find one specific word in a 1,000-volume library, and the only way to read it was to copy the entire library out by hand first.
Precisely. And Mullis realized he didn't need to copy the whole library. The essential insight was this. He could use a pair of short, synthetic DNA fragments, he called them primers, to bracket the exact DNA sequence he wanted.
So the primer basically tells the copying enzyme, the DNA polymerase, exactly where to start and stop copying.
Exactly. And the true genius was in the cycling. He realized if he heated the mixture, the DNA double helix would separate into two strands. Then, as it cooled a bit, the primers would attach to their specific spots. Finally, at the right temperature, the DNA polymerase would just zoom along and copy the target segment between the primers.
But here's where the conceptual leap happened. He realized that the newly synthesized strands could, in turn, become the templates for the next round of copying.
Yes. The process just repeats. Separate, attach, copy. In the first cycle, you get 2 copies. In the second, you get 4. The third, 8. This is the power of exponential amplification.
Let's be really clear about what exponential amplification means, because that's the magic the New York Times quote was getting at. If you start with just one molecule of DNA and run, say, 30 cycles, how many molecules do you end up with?
Assuming the process is 100% efficient, 30 cycles will yield approximately 1 billion copies of that initial single segment.
1 to 1 billion.
That transformation from one molecule to a billion means that suddenly the tiniest trace amount of DNA from a single hair follicle or a tiny blood spot becomes visible and measurable. It was a feat that was utterly impossible before 1983. It turned DNA from this highly limited resource into an abundant one.
And Mullis managed to demonstrate PCR on December 16, 1983. But despite the undeniable mathematical logic, the sources say the staff at Cetus were skeptical.
They were. It was partly methodological and partly cultural. Colleagues were cautious, noting that Mullis's initial results were a bit ambiguous. They pointed to what they saw as methodological problems, specifically a lack of appropriate controls and repetition.
So his execution was maybe a little sloppy, even if the idea was brilliant.
His mind was often ahead of his hands. His supervisor, Thomas White, actually had to reassign Mullis from his other projects to focus entirely on perfecting PCR because the technique was meeting so much internal resistance.
It's just so interesting that this monumental scientific breakthrough didn't solve his personal problems. He said in his Nobel lecture that while all this was happening, he felt lonesome because his girlfriend had just broken up with him.
That detail really speaks to the kind of whirlwind his life always was.
So PCR was invented, the exponential amplification was proven, but the process was still incredibly labor-intensive.
Yeah.
And expensive.
It was. It was an amazing scientific proof of concept, but it wasn't a global workhorse yet.
Which brings us to the critical improvement that made it commercially viable. What was the major practical drawback of the original method?
The fundamental problem was thermal stability. As we said, you need high heat, we're talking near boiling, around 95 degrees Celsius, to separate the DNA double helix into single strands.
Okay.
Well, the DNA polymerase enzyme, the thing that does the actual copying, is a protein, and most proteins, they denature. They get destroyed by that much heat.
So the enzyme was like ice cream in a sauna.
Perfect analogy. It melted. So for every single replication cycle, heating up to 95 degrees and cooling back down, you had to manually stop, open the tube, and add a fresh dose of this expensive enzyme.
So if you wanted 30 cycles to get your billion copies.
You had to manually add the enzyme 30 times. It was tedious, it was prone to contamination, and it was prohibitively expensive for mass use.
You still needed a highly trained technician babysitting machine all day. The breakthrough was intellectual, but the application was still stuck in the age of manual labor.
Exactly. The game changer arrived in 1986, 3 years after Mullis's breakthrough. And it came from another Cetus scientist, Randall Saiki.
Right.
Saiki introduced a DNA polymerase that was sourced from a bacterium called Thermophilus aquaticus. Mercifully, they shortened it to TAC.
And this bacterium lives where?
It lives naturally in the extremely high temperatures of hot springs, like the ones in Yellowstone National Park. It's a thermophile. It loves the heat.
So its enzymes evolved to love the heat too.
They did. TAC polymerase is naturally heat resistant. It could survive the 95-degree separation phase without denaturing. You only needed to add the enzyme once at the very beginning. You could put your mixture into an automated thermal cycler, set it to run 20, 30, 40 cycles, and just walk away. The TAC polymerase would patiently wait for the temperature to drop and get back to work again and again.
That one small molecular detail, the heat stability of one enzyme, fundamentally changed the entire process. It made PCR cheap, fully automatable, and viable for pretty much any lab on the planet.
The impact is, as David Bilder from UC Berkeley stated, just hard to overstate. He called it magical. He said it superpowered molecular biology, and it transformed fields from ecology, where you can now analyze DNA from animal scat, to evolutionary biology, where tiny preserved samples can be amplified. PCR, thanks to TAC, became the indispensable workhorse that made molecular biology accessible to everyone.
The second that technique became automated and commercially viable, the story really shifts, doesn't it? It goes from scientific discovery to a corporate battleground.
Yeah. When an invention can diagnose disease, solve crimes, and generate billions of dollars, the credit lines get very blurry very fast.
Okay, so let's start with Mullis's compensation for this billion-dollar idea.
He received a one-time bonus from Cetus for $10,000.
$10,000 for a foundational technology that would eventually be sold for hundreds of millions? That feels like a massive insult.
It was certainly a source of deep, lasting bitterness for Mullis. But the tension was also fueled by Cetus's decision to bring in other researchers.
Right.
The company, understanding the immense commercial value here, assigned what the sources call top-notch experimentalists, people like Randall Psyche, Henry Ehrlich, and Norman Arnheim, to work on parallel PCR projects.
So they weren't brought in to invent the concept, but to provide the rigor and the data that Mullis, with his, let's say, erratic style, hadn't formalized yet.
Yeah, precisely. They were tasked with generating the critical, clean data to prove the technique worked flawlessly. Specifically, showing that PCR could reliably amplify a human gene, beta-globin, from a whole genome.
And they did.
Psyche generated that data, and Ehrlich authored the first paper describing a practical use of the technique in 1985. Mullis, who was still working on his own paper describing the fundamental process, felt aggressively marginalized.
And he didn't hold back his feelings about it.
Not at all. The sources detail his condemnation of his supervisor, Thomas White, and the members of that parallel team. He referred to them as vultures.
Vultures.
This is the core conflict, right? The inventor, driven by intuition, versus the organization that needs methodological rigor and speed to secure a market advantage.
And the financial stakes were huge. Cetus eventually sold the entire PCR patent, the initial invention, and the crucial Taq element to Roche Molecular Systems for a staggering $300 million.
$300 million. And while Mullis shared the 1993 Nobel Prize in Chemistry with Michael Smith for his conceptual work, that corporate compensation, or lack of it, it just fueled his volatile reputation. It fed his cynicism about institutional science.
Let's talk about the patent challenge, because DuPont tried to contest it, arguing there was prior art from years earlier. Who did they cite?
They cited Nobel laureate H. Gabun Khorana and a Norwegian scientist K. Yell Klepp. Way back in 1971, that's 17 years before Mullis's breakthrough, they'd published work on a conceptually similar idea they called repair replication.
Okay.
Their work demonstrated duplicating and even quadrupling a small synthetic molecule using 2 primers and a polymerase.
So conceptually, the essential elements, primers, polymerase, they were there. Why didn't that invalidate Mullis's patent?
The key was application and context. Khorana's experiment worked on a small, synthetic, highly controlled molecule. It was a very specific chemical environment. Mullis's breakthrough was demonstrating that the exponential nature worked on complex biological mixtures like genomic DNA. That's a whole different ballgame.
And Khorana himself refused to testify for DuPont. He perhaps saw the patent battle as a distraction, or maybe he recognized the huge practical difference between his conceptual demonstration and Mullis's functional application. A jury upheld the Mullis patent in 1991.
But the legal battles weren't over, especially regarding the Taq component.
That's right. In 1999, years after the Nobel, the Roche patent, specifically the part concerning the use of Taq polymerase, was actually found unenforceable.
On what grounds?
It was based on evidence of prior art. There were articles published on the heat-stable polymerase itself back in 1976 and 1980, which predated the work done by the Cetus team that had patented its purification process. It just highlights the layered nature of scientific progress. Mullis had the conceptual leap. Psyche provided the critical enabler with Taq, but the underlying component, Taq polymerase, was already part of the public scientific record.
So the invention that revolutionized biology was the product of a singular moment of genius, years of testing, complex corporate maneuvering, and endless legal battles. What a story. And even if you set aside the patent drama, Mullis's reputation for erratic behavior at Cetus was profound. His supervisor, Thomas White, noted that his behavior was so outrageous that colleagues thought White only kept him on because they were friends. That tells you something about the corporate culture. They tolerated extreme volatility because the genius was just undeniable.
What specifically are we talking about when we say outrageous behavior?
Well, the sources cite specific examples that paint a picture of intense instability. Mullis once allegedly threatened to bring a gun to work.
Wow. Okay.
He engaged in these highly public lovers' quarrels with his girlfriend, who, again, was a chemist working on the same floor.
So uncomfortable for everyone else.
Immensely.
Right.
And the source also details how he nearly came to blows with another scientist at a company party. His emotional intensity just bled over into his professional life, which made him a truly difficult yet indispensable colleague.
He eventually resigned from Cetus in 1986, right after the Taq discovery, but he didn't stop working. He continued inventing and consulting, often blending this high-level science with some really unconventional commercial ventures.
His next stop was a company called Zytron Inc. in San Diego. He was the director of molecular biology there for 2 years. He invented a UV-sensitive ink, a practical chemistry application, but, a far cry from DNA.
Right.
And it was during this period that the source notes he became actively skeptical of the existence of the ozone hole, which was a major environmental concern at the time. This marks a really early concrete shift toward him questioning scientific consensus outside his own domain.
He then transitioned into consulting, focusing on nucleic acid chemistry and becoming this high-profile expert witness in DNA profiling.
A field that, ironically, depended entirely on his own invention to even function.
And this brings us to one of his more bizarre commercial ventures. In 1992, around the time he was cementing his reputation as a DNA forensics expert, he founded a business to sell celebrity DNA jewelry.
DNA jewelry, yeah.
You have to explain this. Amplified DNA inside a trinket.
That's it. He wanted to sell pieces of jewelry containing the amplified DNA of deceased famous people. He cited Elvis Presley and Marilyn Monroe as examples.
That is almost surreal.
It's taking the pinnacle of high-tech molecular biology, the ability to amplify the smallest trace of life, and using it to create morbid novelty items. It just reveals this incredible commercial impulsivity combined with his unique technical skill.
But in the same year, he also founded Atomic Tags, which shows his mind was still operating at the absolute cutting edge.
Atomic Tags was a serious, complex idea. It was a venture to develop highly multiplexed immunoassays using advanced tech, specifically atomic force microscopy, where you'd tag antibodies with heavy metals.
I mean, the goal was?
The goal was to identify multiple disease markers at the same time with incredible precision. So within the same calendar year, Kary Mullis was simultaneously trying to sell Elvis's DNA and launch a highly sophisticated next-generation diagnostic platform. The contrast is just astonishing.
Years later, in 2011, Mullis founded Ultramune LLC to pursue ideas about the immune system. This concept, far removed from DNA synthesis, it just shows his continued ability to conceptualize these innovative molecular solutions. Let's try to unpack this claimed breakthrough, Ultramune.
Ultramune is a highly complex mechanism that proposes to revolutionize immunotherapy by leveraging the immune system's pre-existing memory.
So not waiting for it to develop new memory, which is what a traditional vaccine does.
Exactly. The basic idea is molecular redirection.
So instead of creating new antibodies to fight a new flu strain, you trick the antibodies you already have into fighting the flu for you.
That's it. The core tool is a synthetic chemical linker he called an alphamer. The goal is to divert a robust, pre-existing immune response toward a new immediate threat. The analogy is like this. Imagine your body has a standing army that is already highly trained to fight one specific rare enemy. Let's call them alpha-gals. This army is massive, it's deployed, and it's waiting.
And every human has this alpha-gal standing army.
Yes. All humans have a strong natural immunity to something called alpha-1,3 galactosyl galactose bonds, or alpha-gal bonds. They're found in certain animal products. So the linker, the alphamer, is synthesized with an alpha-gal bond on one end.
Okay.
That alpha-gal end instantly attracts and binds to that massive pre-existing antibody army.
And the other end of this molecular bridge?
The other end of the linker is designed to bind specifically to the new target, say, a surface protein on a deadly new strain of flu, or maybe an anthrax spore. So the alphamer acts as a chemical bridge. It connects the massive pre-existing anti-alpha-gal antibodies directly to the surface of the new threatening pathogen.
So you have literally, as Mullis claimed, fooled your immune system into thinking that the deadly new pathogen is the common safe target it was already trained to destroy.
And that offers immediate mass-scale immunity. That's the theory.
And it worked.
He claimed significant success. He stated the U.S. government paid $500,000 to use this technology against anthrax in preliminary trials. He claimed it resulted in a 100% effective treatment, which was a huge increase from the previous treatment's 40% effectiveness.
Wow.
He was also personally driven to apply it against a pathogenic strep bacterium because it had tragically killed a close friend of his.
This invention just demonstrates that even late in his career, Mullis's capacity for high-level foundational molecular innovation was absolutely intact. He maintained his technical genius even as his personal philosophical views drifted further and further into controversy. And now we arrive at the heart of the paradox. This is the most difficult section to reconcile. Kary Mullis was undeniably brilliant, operating at the highest level of chemistry and molecular biology.
No question.
Yet at the same time, he was guided by this profound and sometimes dangerous skepticism that led him to embrace views that weren't just scientifically rejected, but they carried real-world tragic consequences.
The scientific community actually has a term for this phenomenon, which is highly relevant here. The Skeptical Inquirer coined the term Nobel disease.
Nobel disease. That sounds ominous. What exactly is it?
It's not a medical condition. It's a tendency and an intellectual hazard that's been observed in some Nobel laureates. These are individuals who have reached the absolute pinnacle of achievement in one incredibly specialized field.
Okay.
And having received that ultimate validation, they often begin to believe that their specialized insight and critical genius applies universally to everything well outside their domain of expertise.
So their certainty in one area becomes intellectual hubris in others.
Precisely. They start to embrace scientifically implausible, often marginal or unsubstantiated ideas. And what guides this shift? It's rarely new, rigorous data. The Nobel disease often manifests as adopting views based on anecdotal evidence, conspiracy theories, or personal bias that overrides the very skepticism that defined their award-winning work.
And Mullis is cited as a classic example of this. His ability to synthesize complex molecular data just seemed to vanish when he decided to weigh in on public health or environmental science. Let's start with the most serious implication: his views on HIV/AIDS.
Mullis became a vocal and influential figure in the HIV/AIDS denialist movement. It's a position that placed him in direct opposition to the global scientific consensus. He expressed profound doubt that the HIV virus causes AIDS.
And it's crucial to underscore this point, which really speaks to the Nobel disease. He never conducted any scientific research on either HIV or AIDS himself.
None. His skepticism was entirely philosophical, not empirical.
So what was his reasoning?
In his 1998 autobiography, he explained it was highly anecdotal. He claimed he started questioning the consensus when he was compiling a report and couldn't find a single published reference that definitively stated HIV was the cause of AIDS. A reference he insisted should have been easy to locate if the science was settled. For him, the lack of an immediate, simple citation became proof that the entire scientific establishment was wrong.
That sounds less like scientific inquiry and more like a massive confirmation bias. His personal inability to find the exact source he wanted instantly led him to reject decades of evidence.
That's the danger of the Nobel disease. He published an alternative hypothesis in 1994, claiming AIDS was just an arbitrary diagnosis used when HIV antibodies were found in a patient's blood. He just dismissed the vast complexity of retroviral infection and immune collapse.
And his position put him in alignment with other controversial figures.
Yes, Seth Kalichman, an AIDS researcher who tracks denialism, named Mullis among the who's who of AIDS pseudoscientists. He was a vocal supporter of Peter Duesberg, another molecular biologist who championed denialism.
And this is where the story shifts from personal eccentricity to profound tragedy. His scientific notoriety gave his fringe views a massive, destructive megaphone.
The source material details some very serious implications.
Specifically, the influence he had over the world leaders.
Yes. Mullis's HIV skepticism allegedly influenced the thinking of Thabo Mbeki, who was the president of South Africa from 1999 to 2008. Mbeki, listening to denialists like Mullis, refused to implement life-saving antiretroviral drug programs nationwide. He preferred to focus on traditional, unproven remedies instead.
And the cost of that policymaking, fueled in part by the intellectual weight Mullis provided to the movement, was just staggering.
It's hard to calculate the full scope, but estimates from sources analyzing this period suggest Menelik's policies contributed to as many as 330,000 unnecessary deaths in South Africa.
330,000?
The inventor of PCR, the tool that could rapidly diagnose HIV, became one of the most visible voices denying the cause of one of the 20th century's deadliest pandemics. And that denial carried a price measured in hundreds of thousands of lives. It is the darkest consequence of the intolerable genius.
And his skepticism wasn't just limited to virology. He also took aim at environmental science, expressing disagreement with the scientific evidence for our role in climate change and ozone depletion.
He had a specific cynicism about the motivations of scientists themselves. His perspective was fundamentally conspiratorial. He claimed that theories on these topics were the product of scientists and government bureaucrats conspiring to secure funding.
So a jobs program for scientists.
Essentially, he said, quote, "Science is being practiced by people who are dependent on being paid for what they're going to find out, instead of searching for truth." For Mullis, the consensus on climate change wasn't the result of overwhelming evidence, but a collective economic effort to keep research grants flowing.
To understand the source of this highly idiosyncratic worldview, this extreme skepticism toward consensus, combined with a deep acceptance of personal, unverified experience, we really have to look at his own detailed accounts of altered states of consciousness.
We've already noted his background in chemistry at UC Berkeley. Mullis practiced clandestine chemistry throughout his graduate studies. Specifically, he was synthesizing LSD.
And his friend, Tom White, the one who got him the Cetus job, knew about this.
He was not only aware of it, he cited it as evidence of Mullis's chemical skill. He knew Mullis was a good chemist because, quote, he'd been synthesizing hallucinogenic drugs at UC Berkeley.
That's an incredible inversion. Mastery of illicit chemistry, proving his fitness for a professional biotech job. And he didn't just synthesize psychedelics. He was a very active user.
He detailed it all in his autobiography, synthesizing and testing various psychedelic amphetamines. He talked about a particularly difficult trip on something called DET, and he spoke openly about how important these experiences were for him. He said in a 1994 interview that taking LSD in the 60s and 70s was a mind-opening experience, but what's really significant is the direct connection he made to his Nobel-winning invention.
Right, he said what?
He said taking LSD was certainly much more important than any courses I ever took.
And he made this connection public.
Oh, yes. During a symposium in Switzerland for Albert Hofmann, the man who first synthesized LSD, Hofmann, publicly recounted that Mullis had told him directly that LSD had helped him develop the polymerase chain reaction.
He explicitly credited a psychedelic experience with one of the most crucial scientific inventions of the 20th century.
This profoundly non-traditional path to innovation is just central to his entire story.
And if synthesizing LSD and crediting it with PCR wasn't enough to define his worldview as non-traditional, his interest went even further into the realm of the truly paranormal.
He was definitely open to esoteric ideas. He professed a belief in astrology, for example, which is a pretty big departure from conventional scientific thinking.
But the anecdotes in his autobiography, Dancing Naked in the Minefield, there would really stick with you.
That title alone tells you so much.
It does. He detailed 2 specific paranormal anecdotes that just defy logic.
The first involves a ghostly visitation. He detailed witnessing what he called the non-substantial form of his deceased grandfather.
And what did he do?
He casually offered the apparition a beer.
Offering a ghost a beer. That incredible comfort level with something outside empirical reality, a total suspension of disbelief, is amazing. It's the exact opposite of the hyperskepticism he applied to climate change data.
And the second anecdote is the one that has truly entered the scientific folklore surrounding Kary Mullis. His encounter with a fluorescent, talking raccoon.
A talking, glowing raccoon. Mullis, the Nobel Laureate, detailed this in his autobiography and suggested the animal might have been an extraterrestrial.
The detail itself is just astounding. He recounts being at his cabin in the woods, and this raccoon walks up and starts speaking to him. The raccoon, he noted, was fluorescent. And Mullis didn't dismiss this as a hallucination or some elaborate joke. He integrated it into his reality, suggesting it was proof that reality itself is far stranger than consensus science allows.
This detail just perfectly encapsulates the fundamental conflict in his life. He was a molecular master whose scientific discipline gave him exponential certainty in the lab, yet his personal philosophy was a free-for-all, embracing the most far-fetched possibilities imaginable.
As we conclude this deep dive, the figure of Kary Mullis remains profoundly difficult to categorize. On one side, you have the recipient of the 1993 Nobel Prize in Chemistry and the Japan Prize, honored for providing a technology that fundamentally changed medicine and forensics.
Indispensable technology.
And on the other side, you have a man who wielded his scientific authority to promote scientifically unfounded claims, especially his AIDS denialism, which, through political influence, likely resulted in hundreds of thousands of avoidable deaths.
He was a character defined by these massive contradictory energies right up until his death in 2019 at the age of 74 from complications of pneumonia. We know he loved surfing, he was married 4 times, played guitar, and sang. He was constantly moving.
The story of Kary Mullis really forces you, the learner, to confront the crucial difference between domain expertise and general critical thinking. Mullis was a world-class technician. His ability to innovate within molecular chemistry was peerless. It gave us PCR and the highly innovative ultramune concept. But his skepticism outside his precise field was not guided by the same level of evidence and rigor. When he talked about broader public issues, he was guided by anecdote, personal convenience, and a conspiratorial worldview.
Such a powerful lesson in the limitations of genius when it ventures beyond its highly specialized boundaries. The man who solved the molecular mystery of DNA amplification seemed utterly incapable of applying critical distance to the mysteries of his own mind and life.
And that brings us to our final provocative thought for you to chew on. PCR is a tool of almost surgical precision. It allows scientists to analyze the smallest traces of DNA to determine objective truth in medicine, in forensics, and genetics. It leaves almost no room for ambiguity. Given Kary Mullis's deep personal belief in the paranormal, in astrology, and in a fluorescent talking raccoon that might have been an alien, what does it truly mean when the man who invented one of our greatest instruments for revealing scientific certainty was so actively comfortable embracing the scientifically implausible in his own life?
It makes you wonder if that very willingness to entertain the absurd, to discard conventional wisdom entirely, was a necessary prerequisite for the brilliance that led to PCR in the first place.